Hello everyone. So today we'll continue with module 2 and we will discuss diffusion with an imposed timescale. So we'll look at a new problem where we want to discuss diffusivity, but this is a problem with an imposed timescale. What is that problem? It's a boundary layer in the atmosphere. So it's the atmospheric boundary layer. If you remember, in the previous class, we looked at a different kind of problem. Again, studied diffusivity, discussed diffusivity, but in a problem with an imposed length scale. It was the airflow in a room where we had a heater, a heating element like a radiator placed in some corner possibly, and the imposed length scale was associated with the length scale of the room. So now we are going to look at a problem where the time scale is imposed, not the length scale. The time scale is imposed, meaning the time scale is known. And that problem is the atmospheric boundary layer. So, as you know, the boundary layer in the atmosphere is exposed to the rotation. In a rotating frame of reference, we have a Coriolis force that is involved, right? This Coriolis force is twice the vector product of the flow velocity and the rotation rate. So essentially, it's the Coriolis force F, okay? F is twice the vector product of the rotation rate. Let's call that omega cross V. Okay, omega is the rotation rate and V is the velocity. So we have the Coriolis force being twice the rotation rate and the flow velocity. Although that is not of our concern right now, you just need to understand for now that is where the Coriolis force is coming from. Now obviously this influences the atmospheric boundary layer, the strength of the boundary layer. Okay, and let's represent this Coriolis force by something called a Coriolis parameter. Okay, now if F is the Coriolis parameter, as in small f is the Coriolis parameter, the angular velocity of the frame of reference, say, is f by 2. Okay, so it is a function of the Coriolis parameter, and let's say it is f by 2. And in that case, the atmospheric flows will have an imposed time scale of 1 over f. Now this Coriolis force is a function of the Earth's rotation rate, and it is also a function of the latitude. At different latitudes, you will have a parameter that is varying. This parameter, Coriolis parameter, just for your information, is a very important parameter in geophysical fluid dynamics, and it sort of quantifies basically the Coriolis force. Okay, it is represented through this parameter. Now the time scale is 1 over f. So at a latitude of 40 degrees, the value of f is about 10 to the negative 4 per second. That's the Coriolis parameter value. At different latitudes, you will have different values. If the boundary layer in the atmosphere were laminar, so like we considered for the room, let's consider a scenario where the flow is laminar. Okay, the atmospheric boundary layer is definitely turbulent, but let's say it was laminar. Then it would be governed by a traditional diffusion equation like we saw in the room case, so that its length and time scales would be related by this equation here. Lm squared is of the order of magnitude of the kinematic viscosity times the time. Right? This is again coming from the same equation that we had seen earlier. If the flow is laminar, you have a diffusion equation. If you remember, this is what we had for the room. Right? If I go back to the slide where I have the problem with an imposed length scale, then this is what I have, right? Tm is or order of magnitude of L squared over gamma. It is that same equation which I'm writing now in a different form. Here, remember, the length scale was imposed. But now for our atmospheric boundary layer, the time scale is imposed. So now we are estimating the length scale here in this particular problem. And that is how you get Lm square is proportional to, or it is of the same order as kinematic viscosity times time. Okay, the time scale, meaning the time scale. So the time scale is imposed, we know what that is. It is 1 over f. F is 10 to the negative 4. So time scale would be 10 to the 4, like we have it here. And kinematic viscosity, since air is involved, we know what the kinematic viscosity is, or the momentum diffusivity, which is 0.15 centimeters squared per second. This gives us an LM of 40 centimeters, isn't it? LM of 40 centimeters. So that is the length scale associated with this problem if the atmospheric boundary layer was laminar. Okay, now we know that is not the case. We know that the atmospheric boundary layer is not laminar. Okay, so let's say it is turbulent, which in reality it is. So in reality, the atmospheric boundary layer is always turbulent and with a typical thickness of about 1000 meters, so a kilometer. So let's keep that aside. We know that the atmospheric boundary layer has a typical thickness of 1 kilometer. Let's keep that aside. Now, if you remember from our eddy diffusivity analysis in the last class, we assumed that turbulent diffusion is analogous to molecular diffusion, except the kinematic viscosity or the momentum diffusivity is replaced with an turbulent diffusivity or an eddy diffusivity. So if we replace nu, the kinematic viscosity, by K, the eddy diffusivity, and you substitute K is equal to UL, we made that estimation in the previous class, you will get your LT to be UT, isn't it? So if I go back here, now this is for laminar. For turbulent, LT squared is equal to K times T. So LT squared is K times T because you're replacing the momentum diffusivity with eddy diffusivity and you have a turbulent time scale now, isn't it? So LT squared is equal to K times T and K is UL. So this is QLT and let's use lowercase t, okay, and I have TT. And so one of the LT gets cancelled out and then you get this equation here. LT is of the order of magnitude of U times T, where T being the turbulent time scale. Alright, now in order to estimate the turbulent length scale here, we will need a characteristic velocity scale. That was the same situation which we had in the room case, the imposed length scale problem. Except there, we knew the length scale, we had to estimate the time scale. Here we know the time scale, we have to estimate the length scale. The only similarity is the fact that we still need to identify a characteristic velocity scale. So in the atmospheric boundary layer, the characteristic velocity is approximately 1/30th of the wind speed, with a wind speed of approximately 10 meters per second. These are just estimates. We estimate that U is equal to approximately equal to 0.3 meter per second, like we have here. So then with T equal to 1 over F, which is then T becomes equal to 10 to the 4 seconds, that yields your turbulent length scale to be 3000 meters or 3 kilometers, which is in fact the same order of magnitude as the typical thickness of a boundary layer as we know it. So we are not off in terms of our estimates. We estimated that the wind speed is approximately 10 meters per second. Again, this is all just order of magnitude. So now we know that our estimates are correct. Our order of magnitude analysis is not far off. So essentially it can be argued that the turbulent eddies with a characteristic velocity u exposed to a Coriolis acceleration which imposes a time scale 1 over f, right, must have a size of u over f, isn't it? Because LT, if LT is of the same order of magnitude as ut, then this is LT is of the same order of magnitude as u over f, isn't it? Because T is 1 over f, 1 over the Coriolis parameter, isn't it? Okay, so what does that mean, right? So we can now equate the eddy size and the boundary layer thickness only because in most turbulent flows, the large eddies seem to have sizes comparable to the characteristic size of the direction normal to the flow field. So we saw earlier that when we estimated the turbulent length scale, we got about 3000 meters or 3 kilometers, which is of the same order of magnitude as the typical boundary layer thickness as we know it. Now, the fact that they are the same order of magnitude happens only because it is a turbulent flow. So, the large eddies seem to have a size that is comparable to the atmospheric size, thickness of the boundary layer. Okay. Now, this is always supplemented by experiments, and we can always come up with some kind of a numerical coefficient formula for LT. For example, in the case of a boundary layer, that correlation is given by this. LT is equal to 1/4 U over F. So you can estimate the typical thickness of a boundary layer if you know the characteristic velocity scale and a Coriolis parameter. And in fact, the Coriolis parameter can be known because the Earth's rotation rate is known, and if you can figure out what the Coriolis parameter is at the different latitudes. Okay, so you based on the wind speed, you can find out what U is. So based on all that, you can figure out what a typical thickness of a boundary layer is. And this is only the case. This is actually a real. This is actually reality, meaning this length scale that you estimate is in fact of the same order of magnitude as the thickness of a boundary layer. So this is a good estimate, but this is the case only because it is a turbulent flow. That is illustrated through this picture shown here in this slide. So you have basically what is shown here is large eddies generated through a boundary layer in the atmosphere, and you will see that the thickness of the boundary layer is of the order of magnitude as some of the length scales that you see in this flow, like the one that I have drawn here. It is of the order of magnitude, and that is the same as this thickness of the boundary layer. I hope this is clear now. So now we use the above equations and we'll do this comparison like we did for the room. We will take the comparison of the length scales like you have in the turbulent flow and then in the laminar flow. In the imposed length scale problem, what we did was we took the ratio of the time scales because it is the time scales that we estimated. Here we are estimating the length scales. So let's compare those. Let's take a ratio of those. So LT over LM is the ratio that we are after. LT is U over F, and LM squared is nu times T, isn't it? So if I go back, LM squared is nu times T. So if I use that, okay, and then put it in here, I have LM is equal to nu times T, and LT is equal to, so if I go back again, LT is U over F. Putting that together, again remember it can be 1 over 4, but there can be a 1/4 in there, but we are just doing order of magnitude. So essentially what you have is U over F times F over nu to the half. So that would be U squared over F nu, isn't it? That would be U squared over F nu. That comes from the fact that you have an F to the half and F here, which gets cancelled out, and then you will have U squared over F nu to the half, the whole thing to the half. Okay. Now remember, this comes out to be the Reynolds number, isn't it? Because if I go and think about what F is, it is 1 over T. It is 1 over T. And what is 1 over T? It is U over L. It is U over L. So one of the U's gets cancelled out and I get out of this U L over nu. So F is 1 over T and 1 over t is, or t is L over u, distance over velocity. So essentially 1 over f is t, correct, and which is L over u. So one of the u's gets cancelled out, and then you have a ul over nu, which is re to the half. So essentially re is clearly associated with the ratio of turbulent and molecular diffusion length scales. Okay, except here it is re to the half. So what does that mean? As the Reynolds number increases, my turbulent length scale is increasing. So if I go back to the previous picture, as the Reynolds number of the atmospheric boundary layer is increasing, I have a thicker boundary layer. As the Reynolds number of the boundary layer is increasing, I have a thicker boundary layer. So the turbulent flow penetrates much deeper into the atmosphere because I have a thicker boundary layer than laminar flow. For example, in our case, the atmospheric boundary layer is approximately 10 to the 7. So that gives you an idea what LT over LM is. It is 10 to the 7 to the half. Right? So approximately 1000 and more than 1000. But what this means is you have a thicker boundary layer with increase in Reynolds number. So turbulent flow is penetrating much deeper. So the summary is the fact that with imposed length scales, in the previous problem, in the room problem, Reynolds number is the ratio of the time scales. Okay? It was Tt over Tm. And while in flows with imposed time scales, so let me go back to make sure, it is the ratio of the time scales, isn't it? So we had here, see, it is 1 over Reynolds number is Tt over Tm, or Re is Tm over Tt, because when we are talking about time scales, it is the inverse, right, compared to length scales. So in the imposed length scale problem, Re is Tm over Tt, whereas in the imposed time scale problem, it is Lt over Lm squared. So Re is proportional to the square of the length scale of the problem. So since the Reynolds numbers of most flows are large, we agree that turbulence is far more effective in terms of diffusion compared to laminar motion, compared to molecular motion. And we knew that. That's why we called it enhanced diffusion, right? But this essentially proves that as well. Re is Lt squared over Lm squared in an imposed length scale, in an imposed time scale problem, I'm sorry. So we looked at two different problems, a length scale problem and a time scale problem. And in both those cases, we came up with ratios for Reynolds number. So except in the imposed length scale problem, the Reynolds number was just the ratio of the time scales. So it was actually technically Re is Tm over Tt. Whereas in the imposed time scale problem, it is Lt squared over Lm squared. And so turbulent flow penetrates far more deeper than laminar flow. And again, that is because of the enhanced diffusion, this just proves that. So we looked at two different problems, one with an imposed length scale and one with an imposed time scale. But keep in mind, we just considered one particular time scale, one particular length scale. We very well know that in turbulent flow, you have a wide range of length scales. So isn't considering just one length scale, one time scale is simplified, but it still provided a lot of understanding to us in terms of what turbulent flow can do in comparison to the laminar flow. So that takes us to, let's look at multiple length scales. Let's see what that means. Okay, we know that the fluid dynamics of flows at high Reynolds numbers is characterized by several length scales. The fact that it is turbulent, meaning you will have a wide range of length scales and time scales. So in turbulent flows, the largest length scale is sort of the dimension of the flow. And the lowest is bounded by the scale at which molecular diffusion is dominant. Not the molecular scale, because we are still governed by the continuum hypothesis. So the larger scale represents the dimension of the flow. In the case of a pipe flow, it would be the diameter of the pipe. In the case of an atmospheric boundary layer, it would be the thickness of the boundary layer. In the case of flow between two plates, it will be the distance between two plates. In the case of flow over a cylinder, it will be the diameter of a cylinder. In the case of flow over a flat plate, just like what you have in an atmospheric boundary layer, it will be the thickness of the boundary layer, so on and so forth. So this would be the dimension of the flow field, correct? This would be the largest length scale, order of magnitude. The smallest length scale would be the scales, the smallest scales at which diffusive action, molecular diffusion, is dominant. So because you have a wide range of length scales, you will actually need a spectral analysis to make sense out of everything, right? You have multiple length scales, multiple time scales, you have multiple frequencies. A spectral analysis is required. If you just have one length scale, then all you need to look at is that one length scale, and you don't need some kind of a spectral analysis. But here you will need that. Okay, so keep that in mind. Let's consider a laminar boundary layer first. Okay, we have a steady flow of an incompressible fluid. For the most part of this class, we are only considering incompressible flows. So let's consider incompressible equations, Navier-Stokes equations with a constant viscosity. Again, non-Newtonian is not something we are considering in this class. So this is what you have. It's a steady equation, so the unsteady term does not exist. We have neglected it. We have the inertia term, we have the pressure gradient term, and we have the viscous term. And we can estimate the inertial terms as u squared over L, order of magnitude, and the viscous terms as nu u over L squared. We did this earlier. Because you have one u here, one u here, it becomes u squared, and x here non-dimensionalized becomes L, capital L, and on the right hand side I have a nu, so I would just to make it clear, this is nu, kinematic viscosity, and this is velocity. I have one u here, a nu here, and two x's here, so that becomes an L squared. Okay, so if I were to non-dimensionalize the equation and estimate the order of magnitude of each terms, this is what I would come up with. I have u squared over L on the left hand side, and I have nu u over L squared on the right hand side. So if I take a ratio of these terms, okay, inertia over viscous, which is by first principles, it is Reynolds number, right? So then inertia over viscous, and I see that. So if I take u squared over L divided by nu u over L squared, I do the manipulation cancelling out, and I get nu u over L, isn't it? I'm sorry, I made a mistake there. It's not nu u over L, it is u L. It is u L over nu. Okay, which is the Reynolds number. So that's what I have. The ratio of these terms is UL over nu, which is the Reynolds number. So the viscous terms become negligible at high Reynolds number. We know that, right? Reynolds number is the ratio of inertia over viscous. So at high Reynolds numbers, the viscous terms become negligible. But there is a slight problem here, and we've discussed this briefly, and this is very clearly pointed out in the book of Tennekes and Lumley. If at high Reynolds numbers the viscous terms are negligible, it doesn't mean you can completely neglect it, because boundary conditions and initial conditions make it impossible to neglect it. For example, the boundary layer has to exist in a flow over a flat plate, isn't it? It has to exist in a flow over a flat plate. If you don't have viscosity, then you don't have a boundary layer. The velocity is zero on the plate because of viscosity, because of friction. If you neglect the viscous effects, then that doesn't exist, meaning the velocity is non-zero at the plate, which is not possible. If the velocity was non-zero at the plate, hypothetically, on the surface of the plate, if the velocity was non-zero, you wouldn't have a boundary layer. So neglecting the viscous effects, meaning we are neglecting the no slip condition, which is just not possible. So viscous effects do exist, right? And this can be understood better by allowing the viscous effects to be associated at small length scales. So viscous effects do exist, except they exist at the small length scales. So that is the problem that we are going to be facing when we consider this viscous term here to be at the same length scales as the inertia term. That is not correct. According to Tennekes and Lumley, it is better to consider these at different length scales so that we can understand that viscous effects do dominate, except they dominate at the smaller length scales. In laminar flow, this is not a problem because you have only a single length scale. Whereas in turbulent flow, since you have a wide range of length scale, it is important to understand where the inertia effects dominate and where the viscous effects dominate. So we will look at that in more detail in terms of the varying range of length scales in the next class. Thank you.